Hi, this is Dr. Felicia, Assistant Professor, Department of Mathematics, Sri Krishna Swami College for Women. Today we are going to see the topic groups in algebraic structures. Basics of groups. A set is a collection of well-defined things, objects or elements, and it does not vary from person to person and is represented using a capital letter. Next we'll see binary operation, an operation that contains two elements of a set given another element of the same set is called a binary composition or binary operation. Generally, a binary operation can be represented using a dot or a star. Now we'll see the group's definition. If G is a non-empty set and star is a binary operation defined on G such that the following laws or axioms are satisfied, then G, star is called a group. Let G be a non-empty set and star be a binary operation on G such that the first law, closure law, states that for any two elements A, B belongs to G, that A star of B belongs to G. And associative law, A star of B star of C is equal to A star B star C for all the A, B, C belongs to G. The next one is identity element. That is, there is an element E belongs to G such that A star equal to E star A is equal to A for all A belongs to G where E is the identity element. The fourth law is inverse law. For each A belongs to G, there exists an element B belongs to G such that A star B is equal to B star A is equal to E where B is equal to A inverse, which is the inverse element of A. Next, we'll see the notations of groups. We'll consider a set of real numbers and a binary operation, say addition, then it forms a group and this is represented as R, plus. And similarly, Z, plus is also a group that comprises a set of integers under addition. Next, we'll see certain terminologies of groups. The first one is abelian group or commutative group. G, star is said to be an abelian group or a commutative group, which is a binary operation that satisfies the commutative law, that is A star B is equal to B star A for all A, B belongs to G. Next, we see what is a semi-group. If the set G satisfies only closure law and the associative law, then G is called a semi-closed group or semi-group. The next one is finite and infinite group. In a group G contains only a finite number of elements, then group G is called a finite group. Otherwise, group G is called as an infinite group. Next, the order of a group. The number of elements in a finite group G is called the order of a group and is denoted by O of G. That means that if the number of elements in G is n, then order of G is equal to n. Next, we see the theorems on groups. The first theorem is the uniqueness of an identity element. In a group, the identity element is always unique. That is, there cannot be existing two different identity elements in a group. We'll prove it. Let G, star be a group. Then we assume that E and F are the two different identity elements of a group G. So we'll see the case 1. Let E belongs to G be the general identity element of G. And F belongs to G be the identity element of group G. So from this we have E star F is equal to F star E equal to E, and we'll keep this as equation 1. Next we move on to the case 2. Let F belongs to G be the general identity element of group G and E belong to G be the identity element of group G. For this, F star of E equal to E star of F is equal to F. So from 1 and 2 equations, we can conclude that E is equal to F. That is, in group G, the identity element is unique. There exist no two different identity elements in group. Next, we'll see the theorem, cancellation laws, and this is a very important result in groups. And we have left cancellation laws and right cancellation law. So let G be a group, and for any elements A, B, C, which is in G, we have to prove for left cancellation law AB equal to AC, which implies B is equal to C, and same thing by using right cancellation law, B is equal to C, which implies B is equal to C. So to prove that, we'll first consider a group G and E be any identity element in group G. Also, we consider A inverse is equal to A inverse equal to E. So for proving the left cancellation law, we consider AB is equal to AC. Then multiply A inverse on both the left side of the equation. So we have A inverse AB is equal to A inverse AC. Now by using the associative property, I am grouping A inverse A on both sides. From that I will be getting EB is equal to EC from the equation 1. So which implies B is equal to C. Thus AB is equal to AC, which implies B is equal to C. Hence from this the left cancellation law is proved. Now we prove the right cancellation law. Consider BA is equal to CA and BA into A inverse equal to CA into A inverse. That is multiplying the A inverse on both the right sides. So we have by associative law B of A inverse is equal to C of A inverse. So from this we arrive, since A inverse is equal to E, we have B is equal to C, and by the left cancellation and the law, I will be having right cancellation law, B is equal to C. Thus, BA is equal to CA implies B is equal to C. So by using both the left cancellation law and right cancellation law, many results in groups have been proved. So next we see some applications of algebra. Because of its generality, abstract algebra is used in many fields of mathematics and science. Also, for instance, algebraic topology is uses algebraic objects to study topology. Recently proved point case conjecture asserts that the fundamental groups of manifold which encodes information about connectedness can be used to determine whether a manifold is fair or not. Algebraic number theory studies various number rings that generates a set of integers. Using tools of algebraic number theory, Andrew Wills proved a Fermat-Last theorem. Next, application of group theory, predicting the polarity of molecules. A molecule cannot have a permanent dipole moment if it has a center of inversion, belongs to any of the d point groups, belongs to the cubic groups T or O. Thank you.